Good morning to all. Today going to discuss about quantum numbers. This chapter belongs to first BSc Chemistry in General Chemistry 1 for Unit 1. What is meant by quantum numbers? Quantum numbers are route and mobility of an electron in an atom can be described using quantum numbers. The Schrödinger equation must be met when the quantum numbers of all the electrons in an atom are summed together. Quantum numbers are the values of conserved quantities in the quantum system. Quantum numbers that describe the electrons are numerical quantities that provide solutions to the Schrödinger wave equation for hydrogen atoms. So, now let us see the definition for quantum numbers. A set of numbers used to describe the position and energy of an electron in an atom are called quantum numbers. There are four quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum numbers. Quantum numbers are a collection of four numbers that may be used to obtain all the information about all the electrons in an atom, including their energy, location, space, kind of orbital occupied and even the direction of that orbit. Now, let us see the principal quantum number. Principal quantum number is denoted by the symbol small n. Principal quantum number are designated the principal electron shell of the atom. Since the most probable distance between the nucleus and the electron is described by it. A larger value of principal quantum number implies a greater distance between the electron and the nucleus, which in turn implies a greater atomic size. The value of principal quantum number can be any integer with a positive value that is equal to or greater than 1. That is, the value n is equal to 1 denotes the innermost electron shell of an atom, which corresponds to the lowest energy state of the electron. Lowest energy state means ground state of the electron. Thus, it can be understood that the principal quantum number cannot have the negative value or be equal to 0, because it is not possible for an atom to have the negative value or no value for a principal shell. When a given electron is infused the energy state, that is excited state, it can be observed that electron jumps from one principal shell to the higher principal shell, causing an increase in the value of principal quantum number n. Similarly, when the electron lose energy, they jump back into the lower shell and the value of principal quantum number also decreases. The principal quantum number, the increase in the value of n for an electron is called absorption, emphasizing the photons or energy being absorbed by the electron. Similarly, the decrease the value of principal quantum number of an electron is called emission, where the electron emit their energy. In principal quantum number, the maximum number of electrons in a shell is given by 2n square. Next we see azimuthal quantum number. In the azimuthal quantum number is otherwise known as orbital angular momentum quantum number. This is denoted by the small l. This quantum number describes the shape of a given orbital and its value is equal to the total number of angular nodes in the orbit. The value of azimuthal quantum number can indicate either an S, P, D or F subshell which vary in shape. This value depends on the value of principal quantum number. That is, the value of azimuthal quantum number ranges between 0 to n minus 1. For example, if n is equal to 3, the azimuthal quantum number can take the following values, that is 0, 1 and 2. When L is equal to 0, the resulting subshell is an S subshell. Similarly, when L is equal to 1 and L is equal to 2 means the resulting subshells are P and D subshells. Therefore, N is equal to 3. The 3 possible subshells are 3S, 3P and 3D. Next we see magnetic quantum number, that is denoted by the symbol M. The total number of orbits in the subshell and the orientation of these orbitals are determined by the magnetic quantum number. This number yields the projection of the angular momentum corresponding to the orbital along a given axis. If the P subshell L is equal to 1 comprises 3 orbitals, it is also known as 3 dumbbell shaped clouds. Hence, that the magnetic quantum number of the electron in the P subshell should be either -1, 0 and +1. In similar for D subshell, where L is equal to 2, has 5 orbitals. It is also known as the 5 double dumbbell shaped clouds. That is, magnetic quantum numbers values from -2, -1, 0, +1, +2. That is range between -2 to +2. The value of magnetic quantum number is dependent on the value of azimuthal quantum number. For a given value of L, the value of M ranges between -L to +L. Therefore, it directly depends on the value of principal quantum number. For example, if n is equal to 4 and L is equal to 3 in an atom, the possible values of the magnetic quantum numbers are -3, -2, -1, 0, +1, +2 and +3. That the azimuthal quantum number in S subshell L is equal to 0, that the corresponding magnetic quantum numbers between, that is 2L plus 1. In S subshell, the possible magnetic quantum number is 0. In P subshell, that is substitute in the 2L plus 1, there are the 3 orbits. M values are -1, 0 and +1. In D subshell, that is L is equal to 2 and M is equal to -2 to +2. In F subshell, there are in the azimuthal quantum number, that is in a L is equal to 3, magnetic quantum number M is equal to -3 to +3, that is 7 subshells. The total number of orbits in a given subshell is a function of azimuthal quantum number value of that orbit. It is given by the formula is 2L plus 1. If 1s subshell means, that is n is equal to 1, L is equal to 0. There is 1 orbital. Each orbital accommodates 2 electrons. So, in 1s subshell can hold the 2 electrons. In the 2p subshell, that n is equal to 2, L is equal to 1. It contains 3 orbitals. Each orbital accommodates 2 electrons. So, 2p subshell can hold there 6 electrons. In 3d subshell, n is equal to 3, L is equal to 2. So, it contains 5 orbitals. That is, each orbital accommodates 2 electrons. So, total number of electrons in a 3d subshell is the 10 electrons. It is similar for F subshell. It contains the 7 orbitals. that the 14 electrons are accommodated in the F shell. The last one is the spin quantum numbers. Spin quantum number is denoted as S, small s. The electron spin quantum number is independent of the values of N, L and M, that is principal, azimuthal and magnetic quantum numbers. The value of these numbers gives insight into the direction in which the electron is spinning. The value of S offers insight into the direction of the electron is spinning. The possible values of the electron spin quantum numbers are plus half and minus half. The positive value of the spin quantum number implies an upward spin on the electron, which is also called spin up and is denoted by the symbol upward arrow. If the spin quantum number has the negative value, the electron question is said to have the downward spin or a spin down, which is given by the symbol downward arrow. The value of the electron spin quantum number determines whether the atom in question has the ability to produce the magnetic field. The value of spin quantum number can be generalized to plus or minus half. So, now let us see if n is equal to 1, L is equal to 0, M is equal to 0 and the spin quantum number is either plus or minus half. The first subshell, if the number of orbitals in the first subshell is the 1, number of electrons needed to fill subshell is the 2. So, total number of electrons in the first subshell is the 2. In the second subshell, there are the two possibilities. There is n is equal to 2, L is equal to 0, M is equal to 0, S is equal to plus or minus half. That is S orbital, that is in the 2 electrons are accommodated. If another case, n is equal to 2, L is equal to 1, M is equal to minus 1, 0, plus 1 and the electron spin quantum number S is equal to plus or minus half. That is for the p orbital, it accommodates 6 electrons. So, in the second orbit, the total number of electrons in the subshell is the 8. In the similar way for the third orbit, in the third orbit, there are the 3 possibilities. N is equal to 3, L is equal to 0, M is equal to 0, S is equal to plus or minus half. There is the 2 electrons are accommodated in the subshell. In the N is equal to 3, L is equal to 1, M is equal to minus 1 to plus 1, S is equal to plus or minus half. 6 electrons are accommodated and the third one, N is equal to 3, L is equal to 2, M is equal to minus 2 to plus 2 and the electron spin quantum number is plus or minus half. So, total number of electrons in the subshell is 10. So, in the third subshell there are 18 electrons are accommodated. Let us see the principles governing the occupancy of electrons in various quantum levels. That is mainly for on the Pauling's exclusion principle is one of the important principle along with Alpha principle and Hund's rule in chemistry. Pauling's exclusion principle basically helps us to understand the electron arrangements in atoms and molecules, and it also gives the explanation for the classification of elements in the periodic table. First we see the Pauling's exclusion principle. The Pauling's exclusion principle states that in a single atom, no 2 electrons will have an identical set or the same quantum numbers. To put in a simple term, every electron should have or be in its own unique state, that is singlet state. There are 2 salient rules that the Pauling's exclusion principle follows. First one, only 2 electrons can occupy in the same orbital. The two electrons that are present in the same orbit must have opposite spin, or they should be anti-parallel. For example, neutral helium atom. As a common Pauling exclusion principle example, the atom has two bond electrons and they occupy in the outer shell with opposite spin. Here we will find that the two electrons are in the 1s subshell, where n is equal to 1, L is equal to 0, magnetic quantum number is 0, spin quantum number is plus or minus half. That is different. If we draw the diagram, then the subshell of the helium atom will be represented with one up electron and one down electron. In essence, first 1s subshell will consist of two electrons which have opposite spin. Similarly, for the hydrogen atom, in the hydrogen atom there is one electron is there, that is occupied in the 1s subshell, that is only in the one upward arrow. Then one more up electron in the 2s orbital. What we are trying to depict here is that the electronic configuration of the orbitals is written in this manner. Hydrogen is the one upward arrow, helium is the two electrons are there, that is anti-parallel. In the lithium atom, 3 electrons are there. There are the 2 electrons are anti-parallel and one in upward direction. What is the importance of the Pauling's exclusion principle? This idea contributes to the explanation of a wide range of physical phenomena. It demonstrates how the elements work together to create chemical connections. With the use of this rule, periodic tables are also described. Alpha principle. In the alpha principle states that atomic orbitals that are available and have the lowest energy levels are filled before those that they have higher energy levels. According to this, electrons are inserted into atomic orbitals in ascending order of orbital energy. Germanic in origin of the word alpha roughly translates to construct or built up. Below in a diagram showing the sequence in which the atomic orbitals are filled. Here the terms principal quantum number and azimuthal quantum number represents, that is n and l respectively. The increasing order of the energy of various orbitals is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 5d, 5p, 6s, 4, 7, 5d, 6p, 7s, 5f, 6d, 7p, etc. The limitation of this alpha principle is not followed in two places. That is, 4f orbitals have to be filled up before filling up 4d. But after 6s is completed, the next electron enters into the 5d level instead of 4f level. The next 14 electrons go into the 4f level. Then the remaining 9 5d levels are filled up. Similarly, one or more electron enter into the 6d subshell before an electron occupies in the 5f subshell. Last we see the Hund's rule. Hund's rule states that electron pairing in the p, d and f orbitals in the degenerate state cannot take place until each orbital of a particular subshell has one electron in it or it is solely occupied. This rule explains that each orbital in a subshell fills up once before filling up with the second electron. In singly occupied orbitals, all the electrons have the same spin. For example, a p subshell is made of 3 subshells that are degenerate. Degenerate means same energy level. When these three p subshells are filled with electrons, electrons have to fill all the three subshells and have the same spin. The fourth electron onwards only can occupy the subshell having already an electron and having the opposite spin. Before pairing, the electrons hence have to fill all the empty orbitals. This can be understood from the fact that the electrons with the same energy repel each other. If placed together in the same orbit, they should have more energy to overcome the repulsion energy, which increases the energy of the atom. But atoms like to be in the lowest energy, and hence the pairing of electrons in the same orbital has to be avoided as much as possible. This is an example for Hund's rule. In the carbon atom, there are 6 electrons. In the first orbital is paired. In the second orbital, there is 2s and 2p orbitals. In the 2s orbital occupied the 2 electrons. Another 2 electrons in a p orbital, px, py and pz orbitals are there. In the px orbital contains 1 electron. 2py orbital contains 1 electron. It does not pair in the 2px level. The similar for the nitrogen. In the nitrogen atom, p orbitals occupied 1 electron each in the 2p orbital. That s orbital contained only 1 shell. So, the first and second electrons enter consequently. But p subshell contains 3 degenerate levels which equal energy. So, first electron enters 1 in the 3p orbital, the second electron enter in the second p orbital and the third electron enters in the third p orbital. The fourth electron only comes to the first p orbital, so that pairing takes place. Thus, pairing takes place only after all the available orbitals on a given subshell contain 1 electron each. Today, we have to learn about the quantum numbers and the 4 quantum numbers: principal, azimuthal, magnetic and spin quantum numbers, and also the rules related to for the alpha principle, Pauling exclusion principle and Hund's rule. Thank you.